Hello there. This video is for section 6.1 through 6.3. And the main learning objectives, well, we're going to be looking at the characteristics of 4 different types of distributions. And then for each of those types, we're going to be trying to find the probability of getting a number that is somewhere between 2 values that are given. So I'll show you some examples of those and distinguish the 4 different types of distributions. The 4 different types of distributions are uniform, normal, standard normal, and sampling. So those are the 4 we'll go through right now. All right, top of the list is a uniform distribution. So we're going to explain the characteristics of a uniform distribution and find the probability of selecting a number between 2 values. And that's last sentence I couldn't make it like really clear, but I think with an example or two, it'll be much clearer about what I'm talking about in terms of what I mean by selecting a number between 2 values. Okay, so examples. So first of all, a uniform distribution is defined to be where each value of the variable has an equal likelihood of occurring. Now, normally in every kind of distribution, the big 3 idea is center, spread, and shape. Now, when we talk about a distribution, we say, okay, what's the center? What's the spread? What's the shape? The uniform distribution is a little bit unique in that the center and spread, which we could measure, are not really used very often. So I'm not even going to bother giving formulas for them because it's not what we do with uniform distributions. Uniform distributions are in a situation where everything is equally likely. And I have an example here of a discrete uniform distribution. So discrete meaning there's individual values of x. And this example involves a 20-sided die. If you ever played some games, sometimes they have different sided dice, not 6-sided dice. This is a 20-sided dice example. So there are numbers 1 through 20 on different sides of a die. Each side has an equally likely chance of being rolled. And because there are 20 sides, 100% divided by 20 is 5%. So each die or each number on the die has a 5% chance of being rolled. So here on the x-axis, I have the number. So a number 1 is rolled 5% of the time. Number 2 is rolled 5% of the time. Every value has a height of 5%. So this is a uniform distribution. Notice that the shape is what we call rectangular, right? It's not like starting low and going, to the middle, higher up, and then going back down. It's not skewed. It's just basically all the same height, which they call rectangular. So that's the key defining sort of description of the uniform distribution. It's got a rectangular shape. So we can ask questions about this type of distribution, this uniform distribution. For example, I have A here. What is the probability of rolling a number larger than 12? So larger than 12 would be 13, 14, 15, 16, etc., all the way up to 20. So 13, 14, 15, 16, 17, 18, 19, 20. Those are the possible rolls between 13 and 20, including 13 and 20. So I'm looking for the probability of getting a number between 13 and 20. And so that's the idea here is what's the probability of getting a number between 13 and 20. So there's 2 values. We're looking for the probability of getting something between those 2 values. And we can count each of these as a 5% chance. There are 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 possible outcomes that fit our description, and each one has a 5% chance of happening. So if you multiply 8 times 5%, you get 40%. I do want to show you how StatCrunch does this because sometimes counting is inconvenient or messy. So if I go over to a StatCrunch worksheet and I go to a stat calculator, these are all alphabetical, and you can see discrete uniform distribution right here. So there's my discrete uniform distribution. For my die, the lowest number I can roll on a die is 1, but the highest number is not 10. The highest number is 20. And I can just leave this for the moment. So you'll see that there's the rectangular uniform distribution, 1, 2, 3, 4, 5, just like I have on my paper. I'm looking for the probability that the number is greater than 12. So I'll put greater than 12, hit compute, and you can see the computer here, the worksheet tells you that the percentage is 0.4, which is 40%. So right here on StatCrunch, if you don't want to do all the counting and multiplying yourself, it literally just does the math for you with this calculation. So we know 40% chance of choosing a number greater than 12, which is between 13 and 20. All right, back to my notes. What about a number between 6 and 16? Again, we're going to find the probability. We can count, but I'm going to show you how to use StatCrunch to find the probability of getting a die roll where the number that shows up is between 6 and 16. All right, so that's the probability of getting a number between 6 and 16 between two stated values. So instead of doing a standard, I'm going to do between so that you can toggle back and forth. For between, it keeps the same lower and upper limits, but I want to say between 6 and 16. And that's 55%. By the way, for color-sighted folks, you may notice that it colors red the possibilities, right? So 6 to 16, you'll see all the ones from 6 to 16 are colored red. The other ones are colored black. If that's interesting or helpful. Okay, so there's 55% was my answer for part B, and 40% was the answer for part A. So this is called a uniform distribution, but specifically a discrete uniform distribution because there's individual values of X. You can't roll a 1.5 on a die. It's either a 1 or a 2 or some specific number. You may remember from previous chapters, we also have continuous variables. So I have an example here of a continuous uniform distribution. So my second example right here, I have I'll read out the example first and I'll discuss it. So it says during the day, a bus arrives at a specific stop every 30 minutes. A person arriving at that bus stop will wait an amount of time that is uniformly distributed between 0 and 30 minutes. So unless they know the specific bus schedule and can aim for a particular time, if you just show up, the bus could be right there and you spend no minutes waiting, or you could have just missed the bus and it could be a 30-minute wait or anything in between. You don't really know. So every different amount of time that you could wait is equally likely. This is an example of a continuous uniform distribution because it's not that you're just going to wait 1 minute or 2 minutes or 3 minutes. You could wait 1.5 minutes or 2.7 minutes, or there are a whole bunch of minutes and seconds, etc., that you could possibly wait, not just individual discrete values, but a uniform continuity of values between 0 and 30. And so there's no more like single lines, but it's still got the same rectangular shape. So waiting 0 minutes has a probability up here all the way to waiting 30 minutes, the same probability. The height here is about 0.33, and that's just the probability of any time in the 30-minute interval here. All right, so we're going to try to use StatCrunch to find the probability of waiting less than 10 minutes. Visually, less than 10 minutes would be anywhere from 10 down to 0. And we could literally just kind of add up this these probabilities here to find it. But again, let's go to StatCrunch. Now, this is a discrete uniform calculator. So I'm going to hide this. Oh, or I'm going to expand it and then hide it. Okay. And then I'm going to go stat and calculator. And if I scroll down past discrete uniform, it doesn't say continuous uniform, which I'd rather it say. It just says uniform. It's because a continuous uniform is more common. So they just say uniform in general. So uniform distribution. So there's the rectangular with the filled in stuff. I do have to go from, well, the lower limit is 0. It's possible to wait 0 minutes and all the way up to 30 minutes. So I could wait up to 30 minutes for my bus. And there's the uniform distribution, the sort of rectangular shape here. This is the probability that it's greater than or less than 5. We want less than 10. Now, you may notice that there's no like strictly less than or strictly equal to and stuff like that. That's because it's a continuous distribution, so there's no difference between less than or equal to 10 and strictly less than 10. You get the same result. and equal to 10 theoretically has a probability of 0 because, is it 10.0001 seconds or 9.999 seconds? Anyway, those are esoteric arguments you don't have to worry about. In this particular problem, we're just trying to find, I'll remind you, the probability of waiting less than 10 minutes. So I go here, I put probability less than or equal to, gives you the same answer as less than. I put the 10 in there and I hit compute, and it gives me 0.33. So there's a 33% chance, or 33.33% chance of having to wait less than 10 minutes. So that's the 33.3 right here. And then the next question is, what about between 5 and 8 minutes? So once again, in StatCrunch, you can toggle between or just standard. So between, and I would say between 5 and 8 minutes, I believe, were the numbers in the notes. And that is 0.1, which is 10%. So let's see if I remember the numbers right. 5 and 8 minutes, yeah, is 10%. So those are what we're talking about in terms of a uniform distribution, the discrete version and the continuous version. And we can describe them mostly by the shape, because the center and the spread, not really that helpful, not really used for much. But we definitely want to find the probability of getting a number that's between two set values, like between 5 and 8 or whatever, I guess the first one was 13 to 20 for part A up here. Oops, that was supposed to be in blue. Anyways, let's go on to the next type of distribution. So the next type of distribution is one in which you've probably seen several times before in this class. It's called a normal distribution. And we know the shape of a normal distribution. It's this bell-shaped curve right here, where it's symmetric. It has a clump here in the middle. It tapers off to both sides. So a lot of this is just going to be a repeat of stuff you've already learned, nothing really new going on here. But I will show you, just like I showed with uniform distribution, the defining characteristics of it, as well as how to use a StatCrunch to compute the probability of a value, probability of a number between two given values. All right, so a normal distribution. So right here, I have a description of a normal distribution. Normal distribution for the variable x is symmetrically distributed around the mean. So the mean is always in the center. So right here, the center is where we would find the mean. So we call this the mean. And if you remember the symbols, the nomenclature, we write that with this mu symbol. So the center is the mean. Most of the data is close to the mean. Let me go read my notes over here. In the distribution, the data for the variable x is symmetrically distributed around the mean, with the majority of the data close to the mean. So most of the data is somewhere right around the mean here. Okay, so that's what we mean by that. The standard deviation, which is this little sigma symbol, measures how spread out the data is, with approximately 68% of the data lying between either the mean minus the standard deviation or the mean plus the standard deviation. We call this within one standard deviation, and that was what we referred to as the 68, 95, 99.7% empirical rule, where we discussed what the standard deviation was telling us. And the shape is called a bell curve. So like traditionally with most distributions, when we describe them, we talk about the center, that's the mean, the spread, that's the standard deviation, and the shape, which is called bell curve. All right, let's do an example so we can kind of see it in action. All right, so systolic blood pressure, the blood pressure you measure, the number on top, I think, is normally distributed with a mean of 112 mmHg, which stands for millimeters of mercury, has a standard deviation of 10. Some person is chosen at random to have their systolic blood pressure measured. So I've drawn here the shape of the normal distribution of blood pressure. You can see that the middle number is right around 112. That's the mean of 112. So this number should be about 112 here. And the standard deviation of 10, what that means is if I add 10 or subtract 10, I get a couple of values. Let's see, 112 plus 10 is 122. and 112 minus 10 is 102. So the percentage of data is 68% of the data right here. 68% of the people have between 102 and 122 systolic blood pressure. And so that visually looks like the data clumped in the middle. Right? If you remember your histograms and the height of the bar is the frequency, this is the same thing, right? The higher the bar, the more people are in that category. So you have all these high bars for lots of people being between 102 and 122. How many is lots of people? 68% of the people approximately are between 102 and 122. That's our 68 part of the 68, 95, 99.7% rule. Okay. So we have this person. We choose someone randomly. Somehow we get a random person, and we're going to ask a question. What is the probability that their systolic blood pressure is above 130? So here's 130, and we want to talk about above 130. So 130 or higher would be 130 and anything above 130. I mean, I don't know how high blood pressures go, whether they go to 200 or 300 or whatever. We could basically say 130 to infinity if we want to, right? It's basically anything above 130, although probably at some point it's all zero, right? Maybe 200 is the highest blood pressure that's ever been measured in a human. So everything past 200 is all zeros. I don't know. Maybe I'm just making that up. It's probably much higher. Probably people have in the 300s or 400s blood pressure, but I don't know medical stuff. So I'm just kind of spitballing numbers here. So we're trying to find the probability that the blood pressure measurement is from 130 to infinity or whatever the largest possible value is. So that's trying to find the probability that this 130 that the person we're measuring has a blood pressure between 130 and infinity. So let's go back to our StatCrunch. We have to know the mean and standard deviation, 112 and 10, but we do know those. So I'll go over here. I'm going to hide this continuous uniform distribution, and I'll go to stat, calculator, and normal is for n. And I'm going to have to tell it the mean, which is 112. Okay, to get my computer sec to work, 112. And the standard deviation was supposedly 10. And I'll do a compute, and there's the graph with sort of the middle at 112 and, kind of tapering off. It looks like the graph I provided in the worksheet. I am looking for the probability that the number is greater than 130, right? So looking for the probability that it's above 130. So I'm going to go to my StatCrunch. I want greater than. Same thing with this, like greater than is the same as greater than or equal to. There's the probabilities will come out exactly the same. And I want greater than, not greater than 0, but greater than 130. So greater than 130, I'll hit compute. And the probability is about 0.036 or about 3.6%. And you can see it's shaded in here 130 or above 130 to visually indicate that's the region where we find this random person. Well, we would if they were in that region. We're not going to find them very often because only about 3.6% of the people are going to end up with a blood pressure measurement in this region here. All right, so that was how we do part A, probability that the blood pressure measurement is above 130, and we get something like 0.36 or 3.6%. And then we could do a between thing, like between 100 and 120. So just like before, we can toggle between, and I instantly forgot the numbers, 100 and 120. So I can do 100 and 120 and compute. And there's 100 and there's 120. So visually it shows you these are all the people, quite a bit of people. How many people? That's 67% or 67.3% or 0.673 if you don't want to convert it to percent. So that's the 0.673 right there. That's the percentage that are between 100 and 120. I'll write these numbers down just visually, people can see them. 3.6%. This was 67.3%. but I do have the answers over here just to double check. Let's try a question backwards. So my last question over here on this example is, what range of measurements do the lowest 10% of the people have? So I want to find measurements where people's blood pressures are in the lowest 10% of all people. So somewhere down here would be like the lowest blood pressure measurements, and we want the amount to be 10%. So the result is 10%. We're given the percentage, but we don't know the breakoff point. We don't know the the range of numbers, right? We know it's going from like 0 to something, but we don't know what the something is. All right, so we can do that by just specifying. I'm going to do a standard. I'm going to do that by specifying that the percentage has to be 10%. So 0.10 is 10%. And I want the lower ones, I'm going to change this to less than. So here's where you have this right here. These are the numbers that end up being a total of less than 10%. So all of the people who have, well, 99.18 blood pressure and below, all these people are in the lowest 10% of all people who have their blood pressure measured, right? So the most common is 112. As you move away from 112, it's less common. And if you want the people who are uncommonly low, you'd have to go down below like 99.18. So basically from 99 down to whatever the lowest is. I don't think it's possible to have a 0 blood pressure and be alive, but whatever the lowest is, it's 99 down to, let's just say for all practical purposes, 0 is the range of measurements where you get to 10% lowest. So there I have 99.2. So 0 to 99.2. So this is a blood pressure, right? Blood pressure of, right? So if your blood pressure is between 0, well, I know 0 doesn't make sense, but if it's anything below 99.2, effectively anywhere from 0 to 99.2, then you are on the lowest 10% of people who have their blood pressure measured. All right, so that's the standard. That's the normal distribution. That's the regular normal distribution, which hopefully looks a little familiar, but if not, it's a good time to brush up on what that looks like. And then, of course, we have the calculator in StatCrunch. It just allows us to calculate any of these percentages that we like. All right, very much related to the normal distribution is our next distribution called the standard normal distribution. So for the standard normal distribution, I'm going to zoom out a little bit so we can compare the two of them. The standard normal distribution is very, very similar to just a regular, what we call normal distribution. In a standard normal distribution, we use the letter Z for the variable as opposed to the letter X, which may seem like an arbitrary choice. We use the letter Z, and you'll see why. We have a little formula that converts between X's and Z's, so we want to have a different letter. I don't know why they chose Z, but that's the letter they chose for a standard normal distribution. So letter. But just like a normal distribution, it's symmetrically distributed throughout the mean. The mean is always 0. So for a standard normal distribution, it will always have a mean of 0. And the majority of the data is close to the mean, just like for a normal distribution. The standard deviation is always 1. So standard deviation is always 1, and it measures how spread out the data is. Again, the 68%, 95, 99.7, that all thing holds true. So if I take the mean of 0 and I subtract 1, or the mean of 0 and add 1, I get from -1 to 1, and that's where 68% of the data would be. So same empirical rule applies for the standard normal distribution. The shape is also bell curved. I'll show you in the next page what it looks like. In fact, I'll just flip back to this in a moment. So I'll tell you right here. This is what the standard normal distribution looks like. The mean is always at 0. So that's the mean of 0. It's getting in the way of my Z. So let's see if I can erase that. Yeah. Will you cooperate? Okay. So I'll put a little arrow. if I can draw relatively straight, the mean is equal to 0. And the standard deviation is 1, which means if I go up 1 or I go down 1, that gives me 68% of the data. So that's the same idea as before, where most of the data is surrounded around the mean, and 68% of the data is between -1 and +1 standard deviations. Okay, so let me just read off the last bit of facts about the standard normal distribution. Big three: center, spread, and shape. Center is always 0. The standard deviation, and it's a mean. Center is measured by the mean. It's always 0. The spread is measured by the standard deviation. It's always 1. And the shape is bell curve, just like a regular normal distribution. Some of the differences in a standard normal distribution is this thing right here, where because we use a standard normal distribution where the standard deviation is 1 and the mean is 0, the total area under the curve is always exactly 1, which also means the total probability is 1 and the total relative frequency is 1. So this is one of the things that distinguishes a standard normal distribution from just a regular normal distribution. In a regular normal distribution, this one, for example, up here, the area is not necessarily going to be 1 or anything like that. It can be whatever it wants to be. But in a standard normal distribution, the area is always 1, the probability is always 1, the total relative frequency is always 1. This is a special formula right here. I'll have it on the next page as well. It allows us to convert from any normal distribution into a standard normal distribution. Why would we want to do that? Well, I'll give you an example of that in today's lecture, but we're going to be studying standard normal distributions in quite a bit of different chapters in this book. And so there are different reasons why we'll want to convert a normal distribution into a standard normal distribution. And the formula to do so is right here. Let me zoom in a little bit, so it might be easier to see on whatever screen you're using. The z, which is our standard normal distribution variable, is equal to x, which is our regular variable, right? Minus mu, which is the mean, over sigma. So if you take an x value from your normal distribution, you subtract the mean, divide by the standard deviation, you will get the corresponding standard normal distribution value of z. And that's converting a normal distribution to standard normal distribution. So converting from normal distribution to a standard normal distribution, we use a z formula. There is a formula to convert the other way. If you want to convert from a standard normal distribution to a normal distribution, use this formula right here, although we almost never do that. So I didn't bother boxing it or trying to make it seem like it's equally important. It's used very occasionally, so I guess you can have your notes, but the big one is the one I boxed up here. That's the one that we're going to be using a lot whenever we talk about standard normal distributions. All right, that's a lot of talking. Let me see if I can start working on some examples so you can see what a standard normal distribution looks like and questions about that. Okay, so here's the picture again. Mean is 0, standard deviation is 1, still got a bell-shaped curve, and the variable z on the bottom, it actually measures the number of standard deviations. Notice, since the middle is 0, +1 and -1 is exactly the same as +1 standard deviation and -1 standard deviation. So we actually say the variable z measures the number of standard deviations. All right, let's do example problem number 2. All right, so we're gonna go back to our blood pressure problem. So same data. I got this data off the internet, so we're hoping it's true. Mean 112, standard deviation of 10, as before. And we're gonna convert, we're gonna say, what is the z value? What is the z number for someone with a blood pressure of 92? So blood pressure of 92 means the x number is 92. And we're looking for what the z value is. I guess I didn't retype it here. I thought I did. Anyway, I'll just rewrite it over here. So the formula for the converting is z is equal to x minus mu over sigma. All right, so that's the x minus mu over sigma. That's the one I had boxed on the previous page. So that's the formula to find the z value, the number for z, if we were given just a normal variable value. So x is a normal variable value. They told us it's 92, and they're asking us what is the z value. So now here's where your math calculation comes in. You would just say z is equal to the x value, which is 92, minus the mu, which is the mean. The mean is 112. And then all divided by sigma. Sigma is the standard deviation, and it says the standard deviation is 10. So I do this calculation right there. 92 minus 112 is going to be a negative number because you starting with 92 and you're subtracting a number bigger than 92. You can use a calculator if you want, or you can just say, if you had 92 bucks and you want to spend 112, you'd be short. How much short are you? You end up being $20 short, so it's minus 20. And then the bottom number is 10. And minus 20 divided by 10 is negative 2. So negative 2 is the z value. We'd say z value is equal to negative 2. So that's the example of converting from an x value in a normal distribution into a z value of the standard normal distribution. So how do we interpret this? How do we interpret the meaning of that z value? So we know that 92, which is this thing right here, is 2 standard deviations below the mean. Sorry, I ran out of room there. So that's what the negative 2 tells us. It tells us that that x value that we were given, 92, is 2 standard deviations below the mean, which is pretty far, right? We know if we go plus or minus 2 standard deviations, 95% of all the data. So we're all the way down to the lower 5% cutoff when we're down to 92. All right, let's try a between thing. Find the percentage of data that is between z is equal to 0.5 and z is equal to 2.5. So here we're given the z values. We're not given x values. We don't need to convert anything because we're just told the x values are 0. And the z values are 0.5 and 2.5. So I can go back to my StatCrunch. I can still use the exact same normal calculator to make it into a standard normal calculator. The standard here is a different, it's not a synonym, it's a different meaning altogether. But to do a standard normal calculator, you know the mean has to be 0. And we know the standard deviation has to be 1. So we just manually change the mean to be 0 and the standard deviation to be 1. And now we have, let's just get rid of this thing for the moment. So now we have our standard normal distribution right here. And our question is, what percentage of the data is between z is equal to 0.5 and z is equal to 2.5? Okay, so I'm going to do between, was it, I think it was negative. I got to check, sorry. Oh, no, it's just positive, 0.5 and 2.5, no negatives. So 0.5 and 2.5. Now, this is really a z variable because we changed it to 0 and 1, but StatCrunch doesn't know what we're doing. We're just using the normal calculator and saying we're going to put in z values. So don't get distracted when it says x. It's still z between 0.5 and 2.5. I know it's z because I put the mean of 0 and the standard deviation of 1. And as soon as you do that, we're talking about z variable instead of x variable. So there's 0.5 to 2.5. So there's 0.5 to 2.5, and it's around 0.30, a little bit more than 30% of the data is between 0.5 as equals 0.5 as equals 2.5. In other words, a little bit more than 30% of the data is between 1/2 a standard deviation and 2.5 standard deviations above the mean. All right, so what percentage of data is between 0.5 and 2.5? That's the 30.2%, something like that. Looks like I didn't write my answer, but I know it is right here, 30.2%. Okay, let's do something that gives a little bit of meaning to why we start looking at the standard normal distribution, which seems like a lot of extra work and not a lot of gain. So I'll give you a kind of a classic example of one simple way that the standard normal distribution is used. It actually gets more involved in this, but at this point in the course, this is a good example, at least to get started with the idea of why we use standard normal distributions. All right, here goes. Here's my example. So, American adult men have a mean height of 70 inches with a standard deviation of 3 inches. Again, thank you, Internet, for giving me random facts that may or may not be true. Uh, American adult women have a mean height of 64.5 inches with a standard deviation of 2.5 inches. Hopefully, those numbers are fairly accurate. So my question is over here. A particularly tall man measures 75 inches, and he meets a tall woman who measures 69 inches. Now, both of them are tall because the men, on average, their mean height is 70, right? So we know that if you're higher, if you're taller than 70, that means that you are, taller than average, right? So this man is 75 inches taller than the average, than the mean American adult men. And likewise, the average woman is 64.5 and she's 69. So both of them are tall, right? These are two tall people who met each other somehow. Okay. Which one is more unusually tall? They're both tall, but I mean, obviously the guy is taller than the woman. 75 is bigger than 69. But we oftentimes want to know not just absolutely who's bigger, who's taller in this case, but like relatively who's taller. Like, which one is uh, relatively much taller than their counterparts, right? So, is the man taller than other men, or is the women taller than? I'll show you. I'll show you. We're going to use a standard normal distribution to figure this out. All right. So for the men, we have a mean of 70 and a standard deviation of 3. And we have a 70 inch, we have a 75 inch tall man, which means our X value is 75. And we can convert that into a Z value. So I'll remind you the Z formula. I'll just put it over here on the side. The Z formula is X minus mu over sigma. So our X calculation, our Z calculation based on our X will be the X number minus the mu number divided by sigma. Sigma, we know sigma. Sigma is 3. So let me erase that and put 3 instead. Thank you for your computer for doing that. Okay, there we go. So 3. So that gives me a value. 75 minus 70 is 5. 5 over 3 is about 1.67. You can check my math if you'd like to use a calculator. It's supposed to say 5 over 3. All right, what about our woman here? So for women, we know that the mean is equal to 64.5 and standard deviation is 2.5. And our representative here is a woman who measures 69 inches. So our X value is 69. So we calculate our Z value, 69 minus the mean, which is 64.5, divided by the standard deviation, which is 2.5. So $69 minus $64.50. Looks like I got $4.50 left over. Divided by 2.5. So I don't want to, I could probably do this in my head, but I'll probably equally likely make a mistake. So I'm going to grab a little calculator here. 4.5 divided by 2.5, and that's a 1.8. So Z is equal to 1.8. So this gal is 1.8 standard deviations above the mean, and our fellow here is 1.67 standard deviations above the mean. Which one is taller or more unusually tall? Well, the woman is farther away from the average woman than the man is farther away from the average man. I know that because the woman is 1.8 standard deviations above the mean, and the guy is only 1.67 standard deviations above the mean. So that means the woman is more unusually tall compared to the man. So the woman, I guess I could do this in blue. So the woman here, the man is more unusually tall comparatively. Comparatively. I mean, I guess I should say this just in case it's not clear, but to talk about whether a woman is tall or not, you don't compare her to the men, you compare her to the other women. So compared to all the women, she's very tall, taller than this particular man compared to all the men, right? So for the answer here. So this is an example where we use standard normal distribution, and we can very quickly see that the woman is farther away from the mean of women than the man is farther away from the mean of men. Okay, we have one last distribution to talk about, and it is perhaps the most important one. Save the best for last, perhaps, is what we should have here. In this chapter, 6.1 to 6.3, it's not going to seem like a sampling distribution is the most important distribution. They just introduce it here with a few calculations and a few descriptions, but we're going to be doing a lot of sampling distribution. I'll explain a little bit why in this video, but we will touch on it in other videos for sure, because it is an important distribution. It is also, unfortunately, one of the most confusing distributions. So if you have a little bit of difficulty understanding my description of a sampling distribution, fair enough. It's complicated to try to describe. Oftentimes people don't get it, like really understand it thinking about it the first time because it's just complicated, right? So give it a little try, let it sink in, rewatch this part or read a little bit more on what a sampling distribution is. And after a few after a few attempts at understanding this, hopefully it'll become a lot clearer if it wasn't clear in the beginning. All right, so what the heck is this, supposedly complicated sampling distribution? So here's my little description here of what a sampling distribution is. So first of all, a sampling distribution is derived from an already given distribution. You already have to have a distribution. And then from that given distribution, we're going to create a sampling distribution. So sampling distribution won't exist without already having a distribution, right? So what do? So we take a sample of our given distribution, we measure it. Measurement mean we can measure the mean of it. We can measure the standard deviation of the sample. We can measure the proportion of the sample. We're going to measure something about the sample. And then we're going to do it again. So a sampling distribution is, you got a given distribution. You take a sample of that distribution, you measure it. Then you take another sample and you measure it, take another sample and you measure it, and you keep doing that. And you're doing a distribution of the different samples, right? So each sample is going to be like one value of X, right? Each sample is going to be part of your new sampling distribution. I do need to show you an example, obviously, to make this a little bit more concrete, but that's sort of my first attempt to describe that. With any kind of distribution, we always want to talk about the center, spread, and shape. So we'll do that for this one too. If the original given distribution has a mean of mu and a standard deviation of sigma, which is what we normally use, then the sampling distribution will have a mean that's basically the same as the original given mean. The standard deviation will be different. The standard deviation is represented by this SE. And so the standard deviation of the sampling distribution is going to be given by this formula, sigma, which is the standard deviation of the original distribution, divided by square root of n. And what is n, you ask? Well, n is the size of each sample, right? So we're going to take some samples. We take the same size for each sample, and that's the n we divide by in the formula. And by the way, if you want to know what SE stands for, it stands for standard error. Okay, it's not important to know that. That's just the name for it. And so you can say, if you want to be like cool and use stats language, you could say the standard deviation of a sampling distribution is called the standard error. Right? There's a lot of words there, but that's the SE. The SE is the standard deviation of a sampling distribution. It's called the standard error. All right, let's do an example. So I'll go back to my blood pressure example. It's the example that I come back to several times in this video. So I think I'll just leave it like that. Okay, so we back to our blood pressure thing. Same numbers before. I didn't change anything. So we got this blood pressure measurement. It's got a mean of 112. It's got a standard deviation of 10. This is our given distribution. Remember, a sampling distribution cannot be found unless you already have a given distribution. So this is our given distribution, has a mean of 112, has a standard deviation of 10, has a bell-shaped curve. That's our normal distribution. So what do we do to find the sampling distribution? Well, here's an example. We're going to take a random sample of 15 people. So of all the people that were having the blood pressure, right? All these Americans or whatever the population was, we take a random sample of 15 people and have their blood pressure measured. And then we find the mean of those 15 values. So we take 15 people randomly, have their blood pressure measure, and then we take those 15 values and find the mean. You add up the 15 values, divide by 15, that's the mean. So you add up all the numbers, divide by 15, and you get one number. So this one number is the mean of the 15 people's blood pressure. So this right here is a mean, but it's going to be a value of X. Our variable in a sampling distribution is not going to be a direct measurement of the original distribution. It's going to be some sort of measurement or average of the sample we take. We take a sample of 15 people, we find the mean of those people, and we get 114.5. It's just an example. I'm not going to give you the numbers. I'm just making the example just to help you understand what's going on. So one value of X is 114.5 because that's one average or mean blood pressure measurement of 15 people. So now what do? I do it again. I take another random sample of 15 people. I have their blood pressure measured, and I find the mean of those new 15 people. And suppose the mean of those 15 people is 108. That's another value of X. Then I do it again. I take another 15 people, have their blood pressure measured, take the mean of those other new 15 people, find out what their mean is. Maybe it's a 112.3 or something, right? I keep doing this over and over again. Each time I'm taking 15 people, measuring their blood pressure and averaging their numbers together. And the average is the X value. The average is the variable. So I'm going to do this random sampling procedure, let's say 20 times. So 15 people, 15 people, 15 people, 15 people, 20 times. That will give me 20 X values. It'll give me 20 different means. So now I can talk about the distribution of those means, right? So my data is, my X value is means of 15 people taken at a time. And I can say, okay, what is the distribution of those 20 means? What's the average of those 20 means? What's the mean of those 20 means? What's the standard deviation of those 20 means? What's the shape of the distribution of those 20 different means, right? We're just doing the same calculation we did before, but the X value was weird. It's not blood pressure. The X value is the average or the mean blood pressure of 15 people taking it random. Okay, so let's suppose again, I'm not showing you calculations. I'm just trying to help you focus on the meaning of stuff right here. Suppose we take the mean of those 20 different means, and we got something like 112.4, just as an example. I'm making up the numbers, right? Suppose we take the standard deviation of those 20 different means. Well, it turns out we actually don't need to do all the calculations because we have this beautiful formula that the standard deviation of the sampling distribution is always approximately sigma over root n. So sigma is the population or the original standard deviation, which we know is 10. So that's the 10 here. And then n is the size of the sample. Each sample was 15 people. So I divide by the square root of 15. So this is a formula that will calculate very precisely, very closely, the standard deviation of the sampling distribution, or what we call to as the standard error. So if we take the 10 divided by square root 15, use a calculator, you get about 2.58. By the way, we could have also used the formula that the mean of the sampling distribution is approximately the mean of the original distribution. The original distribution was 112, and you can see that when I did the math with my manufactured numbers, I got approximately 112. I got 112.4 by using my numbers that I, again, not showing you because I just don't want you to be wrapped up in all the numbers and calculations. We don't actually have to calculate the mean of those 20 different means because we know it's going to come out to be approximately the same as the original mean. So that could save us a little bit of time. Same thing, we don't have to calculate the standard deviation of this new distribution because we have a nice little formula that approximate the standard deviation very, very nicely as sigma divided by square root n. So we have now a distribution of these samples called a sampling distribution. And a sampling distribution, I'll just draw a little picture right here. It's going to be a bell-shaped curve. We know that the mean is about 112. So that's the middle. That's the mean. I guess the mean is 112.4 if you want to be more precise, but it's approximately 112. The standard deviation is approximately 2.58. I'll say it's 2.6. So just to make it my numbers a little bit easier. So if I take 12.4 and I add 2.6, or I subtract 2.6, that's plus or minus one standard deviation. 112.4, it looks like I have cat aggro, so 1 second, please. Okay, so I'm adding 2.6 and subtracting 2.6. So 112.4 plus 2.6 will give me this new number up here, $112.40 plus $2.60 will give me, I think, 115. And then if I take 112.4 and I subtract 2.6, so now I got $112.40. I subtract $2.60. It's harder for me to do subtraction in my head. So it looks like I got 109.8 if my math was right. 109.8 is over here. 109.8. And so this is plus or minus one standard deviation. So once again, this is 68% of the data. 68% of the means of the samples are between 109.8 and 115. Okay, so that's the idea here of our sampling distribution. We're taking a sample of a certain number of people, in this case, 15 people. We're calculating something about those 15 people. In this case, we're calculating the mean systolic blood pressure of those 15 people. And each time we calculate a mean of 15 people, that's a value of our variable X in our sampling distribution. So we repeat this process. We take another 15 people, we take the mean of their blood pressure measurements, and we do it over and over and over again. And as we do this time and time again, we develop different averages, different means of 15 people's blood pressures. And each of those averages of the 15 people is going to be considered one data point, and we can talk about how those data points are distributed. We can talk about the mean of those values, the mean of the means of 15 people. We can talk about the standard deviation of the means of 15 people, and we talk about the shape of the means of 15 people's means. Okay, so that's the idea of. See, I told you it was hard to explain. I mean, I've been doing this for a while, and it's still hard to explain. So hopefully, you're getting an idea a little bit about what I'm talking about, or maybe I'm just speaking gibberish, and I'll have to do a better job, and we'll have to work on it some more. We have plenty of time. We do this in several chapters, so we're doing a little bit more advanced than you need to know for Chapter 6 homework. But I wanted to do the opportunity now to first try to explain it to you. All right, let's do a question. Let's do a question on this. So a question is right here. Suppose a new random sample of 15 people have their blood pressure measured. What is the probability that the mean of these 15 people is above 120? So since we're talking about the mean of 15 people, we're talking about the sampling distribution. So what's the probability that a number in the sampling distribution is above 120? Similar kind of question as before, right? Just like we did with other problems, we're finding what's the probability that something is above this or something is between this and this. We're saying what's the probability that the mean of these 15 people's blood pressures is above 120. And we're going to use the same darn calculator before, because the sampling distribution is also normally a normal distribution. It's also got like everything bunched around the middle. It definitely plus or minus one standard deviation is 68% of the data. It's the same calculator as the normal calculator. I just have to be able to put in the correct mean and standard deviation. So the mean is 112.4. Standard deviation is 2.58, which I'll just say is 2.6 because it'll be easier for me to remember. So I'll go over here. I'll put in 112. Just give my computer a sec. 112.4 with a standard deviation of 2.6. And I'll just do this thing. So there's the shape with the middle at 112.4, and standard deviation is plus or minus 2.6. And my question is, what is the probability that it's above 120? Above 120. So I just go over here and I say, what's the probability that, oh, this is between, I do standard. What's the probability that's greater than 120? So there's the probability greater than 120. And the answer is 0.00173. A very, very small percentage, because remember, the standard deviation is much, much smaller. Before, the standard deviation was 10, which meant we had to go plus 10 and minus 10 to get 68% of the data. Now, if we only go up 2.6 and down 2.6, we get 68% of the data. So remember, 68% of the data is between 115 and 109.8. And we're saying, what's the probability that it's above 120? 120 is way above 115 in this little picture here. In fact, if I do another 2.6, if I go two standard deviations, 115 plus 2.6 is only 117.6. I'm well above two standard deviations. I could be well above three standard deviations if I actually wanted to figure it out. That's the big difference between a sampling distribution, is that your standard deviation is much, much smaller, which means your data is much, much more grouped together near the mean, which means calculations like this above 120 are going to have a much smaller percentage. And that's because we're averaging 15 people together. When you average a bunch of people together, the highs and lows kind of balance each other out, and you get answers that are much, much closer to the mean. So by doing a sample and averaging those sample together, by doing a calculation of the sample, you get a much more compact normal distribution, what we call a sampling distribution. I think the number I got here was slightly different than the one I got in StatCrunch, because I think when I did it before, I used the 2.58 instead of 2.6, but it should be very, very close. So that was my attempt at explaining what a sampling distribution is, and an example problem on sampling distribution where we used a given distribution about the blood pressure measurements, and then we took samples from that distribution to create a new distribution called the sampling distribution. Some notes I'll just end the video with for this chapter, for chapter 6. For a sampling distribution, we know that the means, if you take a sample and then you can measure something about the sample. So suppose you take a sample and you measure the means of the sample, they are approximately normally distributed, right? If you take the variances, which is a measure of like the spread, standard deviation is just the square root. So, it's basically a similar kind of calculation as standard deviation, but standard deviation is not normally distributed. The variances are normally distributed, or if you're just looking at proportions, they're also normally distributed. And what's really fascinating is that when you're talking about a sampling distribution, it doesn't matter if the given distribution was normal or not, right? Even if the original given distribution was not normal, the sampling distribution will be normal, assuming we have a big enough sample size. So assuming that the sample size is at least 30, then even if the original distribution was skewed or bimodal or kind of whatever it is, it doesn't matter. The sampling distribution from a given distribution will always end up being normal as long as we have a big enough number like 30. Now, in my example, I didn't use 30. I only used 15 people for my sampling distribution because the original distribution was already normal. Because the blood pressure measurements were already normal, we don't need to do 30 because it's already normal. So we automatically get a sampling distribution that's normal. But really cool is it doesn't matter as long as you take n bigger than 30, it doesn't matter what the original distribution was. It could be all kinds of wacky thing, and the sampling distribution will still be normal, which means when we go to StatCrunch, we can use this really nice calculator and get our answers really fast. There is no calculator for skewed distributions, right? There's no calculator for bimodal or weird looking distributions, right? So it's important if you want to have easy answers to be using something like a normal distribution or a uniform distribution, something that we actually have calculators for. And this is why we really like sampling distributions, kind of guarantees that we can use our calculator to stuff. And a little foreshadowing for the future for later chapters. So I have something here also, just a note for later chapters. If you have a known sigma, if the original distribution that you're working off of, you already know the standard deviation, then we use our formula that I talked about before. The standard error is sigma over root n. And we use what's called the normal calculator, the one I showed you, also sometimes called the Z calculator. However, if we do not know the original distribution sigma, we can still use a sampling distribution with the sampling distributions. Whoops, I was supposed to see in green. With the standard deviation being written as this SE. Come on, computer. There we go. SE is equal to S over root n, where S is the standard deviation of the sample. And we use what's called the T calculator. And if you go back to StatCrunch sometime and you'll look under calculators, you'll see there's something called a T calculator. And we're going to be using that quite a bit when we do not know the original standard deviation. So that's just a little foreshadowing, not in chapter 6 homework, but trying to put it all together for you in a nice place so that you can reference it when you need it. All right, so this video attempted to talk about 4 different kinds of distributions, the characteristics of each, and the probability of selecting a number between 2 values in each of those distributions. The distributions were uniform, normal, standard normal, and sampling. So please reach out if you have any questions. Hopefully this video was helpful or informative, maybe useful, and hopefully I see you in the next video. Have an enjoyable day or evening wherever this video finds you.